All right, I do see it's 7:30. John, would you like to introduce tonight's speaker, please?
With pleasure. Andreas Velten is a member of the physics department, right, Andreas? Assistant? No.
Actually, two departments: biostatistics and medical informatics, and electrical and computer engineering.
I should have looked at my notes. He is not physics, bioinformatics, and medical statistics. So
I do have a PhD in physics. So the degree is in physics, and like the departments are. So it is confusing.
So I'll let you explain how you ended up doing the work that you're doing in a department that sounds unintuitive, at first glance. But just to quickly introduce Andreas and his topic, when I saw this press release, I sent him an email instantly. Many of you are probably science nerds like me, and you've seen stuff like this floating around the internet for the last couple of years. This idea of non-line of sight photography, where you basically capture bouncing photons and use presumably a lot of processing power to reconstruct images seen around corners. That is the work that Andreas does. Very cutting edge imagery, very cutting edge optics and computer processing and that kind of stuff. And Andreas is going to give us a talk about that work tonight. So Andreas, over to you. Thank you.
Thank you for the introduction. So let me actually start sharing here and put this on full screen. Well, are we starting? There we go. So maybe just to speak to that a little bit, like I did my PhD in physics in Albuquerque and was working on ultra-fast optics, building ultra-fast lasers and trying to use the pulses for different applications. And after the PhD, I worked at MIT at the Media Lab in a group that is doing computational imaging, and they were interested in like what I'm doing now. So some of the videos, the early videos I'm going to show were captured at that group, and they were interested in how to use this ultra-fast time resolution in imaging, and so that's kind of my background. And then I've been doing a lot of this kind of computational imaging approaches, which have applications in many fields, and I'm particularly looking at this remote sensing now, but also biomedical applications. Today I'm going to focus on this topic of non-line of sight imaging, and I try to include a little bit more of the earlier things, just to include a little bit more context. This is actually a video that was some of the work we created, some of the first work we created when I was a postdoc at MIT. So this is a video that we captured of a laser pulse moving through this soda bottle. So you can see this is a photo of the bottle, but then this is the actual video we captured. You can see this laser pulse moving from the side through the bottle and then eventually hitting the bottle cap. There. And then you see a lot of light scattering around. It hits the floor. Some of it gets trapped up in this little air bubble. And eventually this reflected light hits the bottom of the bottle again. So, so basically this is a video, but normally in a video you would see changes of objects in the scene, where with this system we had enough time resolution to actually, there's nothing actually moving in the scene. All the motion you see is from the light, that you see the motion of the light that composes the image. Now that's very interesting. At the time, this was very interesting for people in computer graphics who have to model all of these effects, right? And the reason why the image looks the way it looks is because you model all this light transport, and but there's other applications to it as well. So I'm going to play this again. I got like basically this entire video. So it's about 2 picoseconds in each frame, which corresponds to about 1 trillion frames per second. The entire video plays over, I think this was about 4 nanoseconds. I think I got a bunch of questions also, what like you should capture a bullet with this camera. Unfortunately, that doesn't work because of the way the camera works. It can't really capture things that are not repeatable, like a bullet. But also, if you were actually slowing a bullet down this much, it would take at least a few weeks to cross the screen. So in a video like this, you wouldn't actually be seeing much. So basically, we can use this technique, this ability to capture light at this kind of picosecond speed to just analyze light transport. Here's a scene that's a little bit more interesting in terms of light transport. So we have a laser pulse going in here that hits the diffuser here on the side. And as a result, then you can see the light illuminating the scene. So you can see the spherical shell of light that spreads out across the scene and illuminates the different objects. I hope the videos come across well through the connection. So I'm going to play this again. So the light illuminates the toy, and then you start seeing the toy reflection in the mirror, and then you see a bunch of stuff in the scene behind it, right? And the camera only captures black and white, right? And the photo I'm showing you is the same scene in color here. So, but let's look a little bit at what's going on. So the light hits this diffuser, and from there it then spreads out. This basically creates this virtual point illumination. From there it spreads out as a spherical shell away from that point, and then what you're seeing is, of course, the light scattered out of that shell and moving towards the camera. So when it hits the floor, you see it. You don't see it when it's just moving through the air, but when it hits something, you kind of see that. And you see it spreading across the scene, and then you start seeing it hitting the toy. And that's the light that basically just goes from that point, hits the toy, and goes to the camera. And then you also notice, if you pay attention, that there's the toy stays lit up after it's being illuminated, right? The floor is just a thin line of light. The floor like gets hit by the light, and then it's dark again. But the toy actually stays lit up, and that's because of subsurface scattering. The photons enter into the toy. It takes a while for them to come back out. Then you see light that hit the back of the toy and hit the mirror. That creates the mirror reflection, and that goes to the camera. And then you see these weird things on the back wall. One is from the light directly moving past the toy and hitting the back. And you see these kind of concentric circles, right? This is shell of the sphere of light that moves out and that intersects with the wall, and it creates these concentric circles moving outwards. And I mean, I'm going to play the video again afterwards, but what you notice is actually not just one circle, there are two. One of them is this arrow that I'm showing. Let me actually have one of them is due to this kind of arrow shown here, and the other one, and that one has a shadow of the toy in it. The other one is another one without the shadow, and that's from light that hit the mirror and then hit the wall. So there's two circles, one with shadow, one without. And the one with shadow is the direct one, and the one without is this one. And then you see two more circles over here in the mirror, and those are from light that went past the toy to the wall, to the mirror, and then to the camera. And then finally one with a circle without a shadow, that is light that hit the mirror, then the wall, then the mirror again, and then the camera. So let's play all of that again, and I kind of point all those effects. So first, you can notice on the floor here, you see this thin line. That's this illumination shell from the virtual illumination pulse. It sends out a short flash, and it creates this shell of light, and that's what you're seeing. And that starts interacting with the toy now. Here you can see the mirror reflection light up. So light hits off the bounce of back of the toy of the mirror and comes to you. And you can see that the toy itself keeps being lit up even though the sphere of light is already gone, and that's subsurface scattering. And then these are the two spherical shells, right? Here's one. You can see a little bit of the shadow of the toy in that one. This is the other one due to light that hit the mirror and then hits the wall, so it didn't get past the toy, so there's no shadow. And then here are the other two. Well, okay. Okay, let's play it again. So toy, mirror reflection of toy, and then shadows, and here's the other ones in the mirror with the shadow and without the shadow. And of course, they all happen at different times because it takes light different amounts of time to complete all these paths. So basically, just by the timing of things, you can figure out how long the light had to travel to complete this trip, and that helps us to get more, to separate all these different light transport components, right? So the goal is always you want to be able to separate your image into direct light and indirect light and all the different components that travel different paths. Here's a quick insert, since we're speaking in astronomy, this transient light transport, there are a bunch of examples of astronomy applications that I'm aware of. I have two here, and of course, in astronomy, this is much easier to see, right? Because you're dealing with larger distances. So what happens here in a few nanoseconds in an astronomical timescale would happen like maybe over days or months or years, right? So there's two effects in astronomy that actually have propped up in papers related to this, and people have talked about this a lot. One of them is like, let's say you have a supernova. So your light, your sun explodes and sends out a fairly short flash of light. And we are on Earth here, this is us. And we want to look at the supernova, but of course we only get to see it from one direction. So there is a paper there where people try to answer the question of how isotropic are these, right? So when the star explodes, is it going to emit the same brightness in all directions, or is there a variability in it? And of course, if you only see every supernova from one direction, you can't really tell. So what these people did was they looked at the reflection of the supernova of nebula close to that system, and this happened a little later, right? And then you can, if you time them right, you can find them and then try to make like a 360-degree or around emission reconstruction of the supernova to see whether it roughly emits the same light in all directions, right? It's kind of funny when you read these papers after working on this nanosecond stuff for a while, right? In this case, the pulse width, which in our case is like a few picoseconds or 10 to the minus 12 seconds. In this case, their pulse was in the order of months, right? Because that's how long the supernova sends out this flash. And then it takes a while, many years, until these nebula light up often. But yeah, so this is basically the same concept. You want to know whether your light source, like you want to see the back of that supernova, right? Another application that I'm aware of where this kind of transient information is important is that if you have a light flash or some event reflect off an interstellar nebula, let's say there is kind of, okay, this is a very straight nebula. It's just an example. So basically our Earth is still over here, and we have this object here that reflects this light from the supernova. And what you see is just at this given time here, when this shell intersects the thing, we just see this bright spot, right? Just like our spherical shell intersecting with the floor, you only see the part of the nebula that's lit up at that time, right? And then as this shell moves out, you see another spot light up. So what you see from Earth is this bright spot moving along the nebula, like this, and the speed, the apparent speed of motion of that spot just depends on the geometry, right? As the nebula is a little tilted, it's looking like moving faster. And if you just tilt these things, right, you can easily make it look like this spot is moving faster than the speed of light. So I think there were a few observations where people reported things that appear to be moving faster than the speed of light, but it's really just this kind of effect, right? Another way of thinking of this is if you, let's say you have a lighthouse inside of a sphere, and you basically, your lighthouse projects light onto the side of the sphere, and you look at that lighthouse spot moving. Now, the larger the sphere, the further away you move the wall, the faster that spot is going to appear to be moving. And then if you make the sphere large enough, at some point the spot is going to appear to be moving faster than the speed of light. But of course, there's nothing moving. It's just that different parts of the wall are lit up at different times. So your brain infers some sort of motion there, but there's no object moving. It's just like different things lighting up in sequence. And that can happen faster than the speed of light, right? There's no information flowing between the different objects. So these are the two. I just put them in very quickly because these are astronomical things that have to do with this transient light transport that I'm aware of. I'm sure there are many more. But so what we want to do with this transient information was the idea, one of the applications, and the one that I'm kind of focusing on today was this ability to see around corners. So imagine you're standing outside this room here with your imaging system and camera, and you want to know what's inside the room, but all you can see is this boring white wall here. So the objective is to be able to send light into the room. If you send a light pulse here, to reflect off the wall, travel into the room, and the light would then eventually come back to the wall, and you would like kind of look at the patterns that this light kind of makes when it comes back out. And from those images, you want to reconstruct an image of the room. Here's an example of a photo of the scene in our lab in our reconstruction of that scene. So the goal is to reconstruct an image of the hidden scene through this indirect illumination, and basically to see around corners. And so the way we do that is we send a short light pulse onto a point on the wall. And then we have a camera that images or is also focused on the wall and images different pixels on the wall. Like, for example, this blue spot and this red spot, right? And then, of course, the light that's sent off this wall is going to travel off the wall. It can't really travel directly to the camera. It has to basically bounce off something else. So it's going to travel into the scene, bounce off like parts of the chair or something else here, and come back. And then our camera is fast enough to actually record the arrival of the light as a function of time. And then you're going to see all these different peaks. And well, those peaks are due to the different parts of the scene, right? Maybe one of the peaks is, I mean, the first peak would probably be the part of the chair here because that's fastest. But then, of course, the time here when the peak happens depends on the total distance traveled, right? So basically, the time it takes for the pulse to go from the wall to this chair to the camera pixel, that basically tells you how long it takes for the camera to actually see the light. And you can see that that distance is different for the different camera pixels, right? So for example, for the chair, it would take a little longer for it to get to the blue spot than it takes for it to get to the red spot. And that's why the peaks are all happen at different times. So that's the kind of information we work with. Of course, we can scan our laser across the entire wall. All the points on the wall are available to us. And we can also have a camera that essentially images all the pixels on the wall. So that's the information we could capture. And the objective is, from that information, we want to reconstruct an image of the hidden scene. So I'm going to go very briefly over the one way we have developed to do this reconstruction. This one is actually inspired by a regular imaging system. So here's an example of the data collected. So you send this pulse to the relay wall, and here's an example of what you would collect with a camera that looks at all the different pixels on the wall. Right, so it's basically the X and Y on the wall and time. So it's basically the stuff coming back out of the hidden scene as a function of time. Now, one way to interpret this information is that this is like an impulse response of the scene. So if we're excited with an impulse from a location, and we're looking at what comes out of the scene as a response to this impulse, and now you can use a little bit of signal processing, and you know that if you have an impulse response of a linear system like the scene, you can use that to compute the output of the scene to any input. So if you basically say, okay, I want to use this captured impulse response to compute what would come out of the scene if I want to send a wave in there, like a camera flash or something, and you just have to convolve it with this excitation function and get this waveform out. So basically, this is the wave that would come out of the scene if you send like a pulse of that wavelength, like an ultrasound pulse or something in. And well, why do we do this? Well, the reason for that is because you know how to reconstruct an image from a wave, right? I mean, this could be a phased array microwave imager, or a phased array radar imager, or a phased array ultrasound imager, or a gravitational wave imager. Imaging from waves always works the same, and we know the mathematical operator that does that. So we just implement that. It's called the Rayleigh-Sommerfeld diffraction integral. So we have a captured signal, we convolve with the kernel, we get the wave, and then we project it back into the scene. And the diffraction operator that does that is called the Rayleigh-Sommerfeld diffraction operator. I'm actually probably not going to go into too much detail about that right here, unless if you have questions later, we can go over this. So it's back to the hidden room. We capture the signal, we convolve it with this kernel, because this is our impulse response. We convolve it with this wave kernel, and then we get this kind of, we call this the phasor field, because it's basically the electric field at the relay wall. And we basically say, okay, this is basically now what we capture at the aperture of our detector, the virtual detector, which is at the relay wall. And we would like to reconstruct an image from that. And then we just treat this like we would treat any wavefront captured with anything, right? This could be a bunch of radio telescopes capturing radio waves and then combining them in a phased array, or it could be a bunch of gravitational wave images that capture the wave at all of these points, or it could be ultrasound probes or anything. So once you know the wave at this surface, at the relay wall, all you have to do is implement this wave diffraction operator in order to project back and reconstruct the image, right? And that works the same for every wave. You don't really have to know whether this is ultrasound or gravitational wave or anything. You just apply this operator and it'll work. And in our case, we just kind of created this virtual wave in order to be allowed to do that here too. So one way to think of this is that we kind of create a virtual camera, right? We have our imaging system and we can now pick a patch of wall somewhere and say, okay, I would like to put a virtual camera, project it onto that wall and reconstruct the image or the video that virtual camera on that wall would see. And one of the interesting consequences of that is that we don't have to limit ourselves to just reconstructing the scene. We can actually make a video of the scene, right? Because our virtual camera might as well just collect a video of this virtual light pulse that we created moving through the scene. And that's what's going on here. Make sure you play this from the beginning. So this is the reconstruction of the scene. You can see this is a photo. There's a chair over here, the bookshelf behind it, this kind of box with the posters over here, and then this whiteboard is in the back. And then like there's a bunch of stuff here that's covered by the other scene part. So there's a shadow. You can't really see this directly. But so rather than just having this 3D reconstruction, we can also make a video of this virtual light pulse we created moving through the scene. And that's going on here. So basically you can see this light illuminating the chair and illuminating the shelf, illuminating this poster box. Then the chair lights up again, which is interesting. And then eventually this shell of light again moves over to the to the board and to this whiteboard. And we see that. So, and then you see this kind of weird illumination effect moving all across the scene. So in a way, we have gone full circle with this, right? So we basically started with a really fast camera and a laser pulse that can capture the motion of light. And then we said, aha, we can use this information to actually have that camera pointed at a wall and reconstruct what's around the corner, right? And then we said, oh, well, our algorithm can actually now create a virtual around the corner camera that can capture the motion of light in the hidden scene, right? Which means we can actually, we basically just now can go play the same game we did with a Coke bottle and do this thing again and follow back all the bounces. So basically, when we play this video of this virtual camera pulse now in the hidden scene, illuminating the scene, we can see that like the first thing that you see is it lights up the chair. Then it lights up these poster boards and this shelf. And then, as I pointed out in the video, the chair lights up again. And that's light that from the wall hit the chair, then hit the wall and hit the chair again. So that's 5 bounces, right? It comes from the imaging system, which is somewhere over here. It hits the relay wall, then it hits the chair, it hits the relay wall again, and hits the chair again, then the relay wall again, and then it goes back to the camera. So that's 5 bounces. So that's what we reconstructed there. Then you see the third bounce of the whiteboard in the back, right? It takes a while until the light gets back from there. And then eventually you see this weird stuff that washes off from the side, and that's actually light that bounced off the side of our lab, which is kind of barely visible over here in the photo. And then washed across the scene. So that's a 4th bounce. So that basically went from laser to wall, to the side wall of the lab, to the shelf, back to the wall, and to the camera. So I'm going to play this video again. And again, this basically just, again, visualizes the light transport. What is illuminated by the light at what time, except that it's around the corner now. So we don't see this scene directly. And of course, the quality is a little worse than the soda bottle before. So actually, let me play this again. There. So the chair lights up, then the bookshelf lights up, and the poster board, and then, as I said before, the chair lights up again. So that's our fifth bounce, right? So that's light that went from the wall to the chair, back to the wall, into the chair again. And then eventually this white board in the back lights up. And then you see this fourth bounce light that comes from the side and kind of washes over the entire scene. So this was a result. Oh, we still cite the archive paper from 2018 here. This paper was published in Nature, and I think it actually came out 2019. If you don't like the archive one here is like that one is for free download. I don't know. I don't know whether the Nature one is open access. At that time, it took us this quality is not very good yet, and it took many hours to actually collect one of these data sets. Here's another example showing that we can actually image quite far in the distance. So this is basically n at 1 meter. There's a disk further back. We couldn't go further out because like the doorway here occludes quite a bit of the light. So the rest didn't look very good, but we could actually see signals from all the way from the back wall here, which is 7 meters away. So you can actually see that this actually works for a reasonably sized hidden scene. So basically then we went, so basically why did this take so long? There's two answers, two reasons for that. A is that it just took a long time to compute the reconstructions, as was said earlier, that there's a little bit of computation involved. So in order to make this faster, we had to speed up the computation. And the second one is it took a long time to collect enough light, to capture enough photons, to actually have enough signal to reconstruct the scene. So in order to make this real time, and this paper that came out this year was about like making a real time imaging system, we had to solve these two problems. So the first one, the speed, was actually solved by us noticing that this diffraction operator, this wave propagation operator, has very fast existing solutions, and we can just, with this formation that we basically express this as a wave propagation problem, we can just use those existing solutions and compute this thing very fast. So in our case, this simple scene reconstruction here in MATLAB took about 1,300 seconds in a single thread. With this new phasor field algorithm, it took 2.8, and that's in MATLAB, which is kind of slow. And this more complex scene, larger scene, took about 8,000 seconds in C code for our old reconstruction algorithm. This new, like more advanced algorithm, which again is basically something that's used in many wave imaging, like digital holography or ultrasound. You can use it again to reconstruct any kind of wave imaging system. And in this case, it takes 25 seconds. So we implemented this on a GPU, and that went down to 0.06 seconds, and that's then fast enough to actually reconstruct it at a reasonably high frame rate. So basically now can reconstruct this at video rates with this new algorithm. And that was a Nature Communications paper that came out a year after this Nature paper. Here's a picture of our imaging system. So there's galvos here. This is a laser head, and there was a single pixel detector here that collected the data. So in this case, we actually had our detector look at a single pixel of the wall, and we would scan the wall with the laser point by point. This was the first collection. Here's a picture of the lab, and here is an example of a simple hidden scene that's fairly close to the relay wall in this example. One thing that we did is we showed that we can actually relatively easily do this with the dynamic relay wall. So if you move the relay wall, that doesn't really hurt us, because we can easily just like keep track of where the relay wall is using our information. Here's an example of a scene being scanned with a single pixel system, and our relay wall now is a curtain with a fan blowing at it that's moving. And you can see this is like the geometry of the relay wall, which is not flat at all. If you just try to reconstruct this and ignore this geometry, then you get nothing. But what we actually do is, from the direct reflected light from the scene, you can estimate the geometry of the relay wall, which is these 3 points. And if you these green points here, and if you include that into your reconstruction algorithm, you actually get a decent reconstruction of the scene. And that works like if your imaging system is moving relative to the relay wall, or if the relay wall is deforming or moving relative to you. So we don't have these problems, but in order to deal with motion in the scene, we really just have to capture more light, right? So it can't, like in this case, you can see a single scan takes almost a minute to complete. So if the scene was moving in that time, we couldn't really use that. And that gets us to like the way we actually detect the light. So the detectors we use are called single photon avalanche diodes. Basically they're photodiodes with a high reverse bias, so that a single photon hitting them will actually create enough current to be detected. So you can think of these as working like a Geiger counter for photons. So the pixel, whenever it detects a photon, will send out a little impulse. Like this is just a logic pulse, and then it's blind for a little bit while it's being reset. And basically, so out of the detector, like out of the Geiger counter, it gets this little clicks whenever it detects a photon. And with that, together with the timing from the laser pulse, you can actually create these reconstructions that we have done. But the problem is it's only a single pixel. And if you think about what that means for a signal, it's not good, right? Because the problem is if I send my laser, my signal to a laser spot on the relay wall. So in this thing, the relay wall is over here, right? This is a relay wall. These green points kind of indicate where I can shoot my laser, right? And I just scan that. And then I look for the single pixel detector. Now, if I send light to a green spot here, I send a lot of photons to this green spot, and some of them make it into the hidden scene, right? But very, very little actually makes it back to that blue dot, right? And if all the other light that hits all these other points here on the relay wall, even though they're being imaged perfectly fine onto my detector, all of them I throw away. So the key to capturing light quicker is to, rather than having a single pixel here, we need an entire camera. We need an array in order to capture all that light that comes back from the relay surface simultaneously. So we actually worked with a group in Italy that builds these SPAD arrays to actually make larger arrays in order to be able to capture this faster. And of course, the amount of signal you can capture is proportional to the number of pixels. So this was like what I showed you was like hours capture with a single pixel. Now we actually have this. Oh, this is the same. Basically, we have a 16 pixel sensor. Now, these detectors actually, you might think this is like a super expensive technology that nobody that you can only afford in the lab or for non-commercial purposes. But these SPAD arrays are actually making their way to mainstream. So SPAD array cameras are in LiDAR systems. This is Voxtel. This is basically for automotive sensing. You can put them on drones. And the latest iPhone 12 and 13 have a SPAD pixel array for LiDAR on the phone, actually. This is actually I think it's a fairly high resolution, more than 100 by 100 pixels. So these SPAD arrays do exist. We just had to make one specific for non-nanosite imaging. So we designed the 16 by 16 pixel SPAD array. We designed a 1 by 16 by 1 pixel and a 16 by 16 SPAD array with this group in Italy. And well, I think maybe if you want to see know these details, maybe we can talk about those a little later. But we basically, yeah, so the pixel has 15 micron size, and the results that I'm going to show are captured with 2 of the 16 by 1 pixel arrays. So basically, we swap our single pixel detector with one of these arrays that has 16 pixels. All right, 2 of them. So we have 28 or 32 pixels in general, but we only use 28 of the pixels actually that we can use. The 16 by 16 array, we're still trying to get to work. So that's in the lab. We're going to have results with that, hopefully sometime later this year. That's actually what's shown in the picture here, the 16 by 16 pixel array. So what I'm showing now is what we were able to do with 28 pixels. And again, the goal is for 28 pixels really that you're just 28 times faster. So here's an example for 7 pixels. So basically we have these, in this case, it's a 7-pixel array on the relay wall. The green are the pixels where we collect the data from. And we basically still scan our laser, right? But now each of the individual pixels collects enough light to do a reconstruction. So in the same time that we, before run a reconstruction, we can do 7 now and add them together to get a better SNR. So basically we confirmed here that, like, yeah, if you have 7 pixels, I can basically get the same reconstructions in 1/7 of the time. So with 28 pixels, which means I should be able to speed up my capture by a factor of 28. We also, I think, did some improvements on the reconstruction to be able to deal with a little more noise. And then we actually were able to do this in real time at 5 frames per second. And that's basically a video of this recent paper that we did this year. So this is actually now, again, the imaging system in operation, scanning the relay wall. This is a laser here. It's a green laser. And on the computer, you see the live reconstruction of the hidden scene, right? And this letter 4 is in the hidden scene. You can see there's we put this little curtain in between. So there's no direct line of sight between the imaging system and this 4. It really has to bounce the light off this white surface in order to get any signal from this 4 in order to reconstruct it. And to show that this reconstruction is currently going on live, like the student here, his name is Jihan Nam. He is going and moving the object, and you can see that it is moving along with this with the real scene. We only, in this case, the hardware only allowed us to go up a certain distance, so we only reconstruct this small volume on top of this black curtain. So if you move things further away, they just disappear because that part of the volume is not captured. We're doing some exercise here. There's a toy that he throws up. And then this is an interesting demonstration. If you work with 3D scanners or LiDAR at all, you know that one of the big issues in 3D scanning is that it's very hard to capture specular surfaces. But you can see for the non-line-of-sight system, it can actually see this mirror surface just fine and reconstruct it in 3D. And it almost looks the same whether you look at the mirror surface or you look at the back of the mirror, which obviously is diffuse. And also you can do this with the lights on, and the system works with the lights on. It looks a little noisier, but it's hard to actually tell on the screen here. So this is something that like a normal LiDAR scanner that would try to do this line of sight would have real trouble with. They would just see what's in the mirror and not be able to actually reconstruct the reflective surface. Okay, there's more toy. And this is another demonstration to show that we were able to create a reconstruction where the signal to noise ratio and the signal level is roughly constant if you move further away, which of course is important if you want to extend this to larger scenes. You would like to be able to reconstruct things that are further away. And you can see within this volume where we're able to reconstruct, the SNR is fairly level. And then we just did some more demonstration here. So this is Jihan getting the letters N, L, O, and S out of a box. You can see here again, like without the correction, you can barely see the shelf in the back. But like once we apply our correction algorithm, they both like the things in the front and the back show up roughly at the same quality. Here it's more exercise, but with the wall in the back, you can see there's a shadow on the wall. this is just a kind of resolution target. So you can see the resolution a little bit as things go further away. And you can see as you go further away, the resolution does decrease, just like in a regular camera. It gets worse and worse. Like the angular resolution is constant, but the actual absolute resolution, you can see this things start blurring together. This was one example of like where you actually need the fast camera to be able to see this milk being poured, and you can see this a little bit here, that you actually see the milk pouring into the box. Here is another one where basically switches on a light and then takes off his coat. Again, the goal was just to demonstrate a few things that need the fast imaging device. And of course, the switching on the light is interesting because, I mean, this. So the reason why the switching on and off of the light. Yeah, there. So the light switches on, and you can see that the reconstruction barely changes. And the reason why that happens, of course, is that so we filter out the ambient light, the room light. There's a narrowband filter that only transmits the green light of the lasers. So we don't see a lot of the ambient light. And what you see is basically due to the active illumination of the laser, right? So we see the scene illuminated from the relay wall. And really these ambient light sources are not that visible to the system. So these are our preliminary studies with this new sensor. So basically this was done with 28 pixels, right? So we were able to do 5 frames per second. It's still quite noisy. We'd like to do to capture more light. But the key to that is really just to add more pixels, right? So as I said, the iPhone already has a sensor that has, I think it's 128 by 192 or 200 or something. I don't know. I don't remember the exact resolution. Unfortunately, that sensor, first of all, it's not accessible at all. You can't actually get any data off of it. You can't hack into it. But also, it doesn't have the time resolution, some of the features we would need to do non-line-of-sight. It's just a good way to show that like these sensors don't have to be expensive. You can like they wouldn't be in an iPhone unless they can be made for, let's say, less than $100 per sensor. So we actually had, for Nonnanosite, we had to work with the company or the research group that makes that does research in these SPAD sensors, and build our own. So the biggest we could do was 16 by 16 pixels. Now, of course, in the future, the plan is to increase that and to get better SNR and allow larger standoff distance, larger scenes, maybe better resolution. Just to give you an idea of where the SPAD arrays cameras are going. So the iPhone sensor, as I said, is a few hundred by, like, roughly 100 by 100 pixels. Canon just announced a SPAD array that's going to be 3.2 megapixels. The research group, some of the research group we're working with kind of shared their roadmap. They want to have 16 megapixels by 2024. So we've done a lot of, besides this Nonnanosite, we've done a lot of stuff with these single photon cameras. I think they could actually also be interesting for astronomy applications. If you have a lot of exposure time available, an EMCCD is still better than these. But if you're worried about timing, motion, like you want to do lucky imaging or something, the SPADs, I think, do really have potential to be better. They're not yet. Today, the ones you buy still have flaws that'll make it problematic. But and I think they're getting better and better for this. So here's our 16 pixel SPAD. We did the same experiment. We scan the A scene, which is a letter 2 here, and then show that in the time for a single pixel system it took to create one reconstruction, we can now reconstruct 256 separate ones. And then we just have to add them all together in order to get the reconstruction. So we've done that. We confirmed that the signal is there. We just haven't. Now we have to write an algorithm that actually handles all the data and actually does the reconstruction in a more meaningful way, because we really can't when we can capture this data really fast, but we really can't run the reconstruction algorithm 256 times. So we have to come up with something smarter for the reconstruction. So here's the laser head, laser controller. So this is basically optimizing the detector, and a lot of the electronics on this card here, like all this is all the controllers for the spat array. There is this is, I think, the hydro harp that that does the counting. All of that is now inside this gray box here. Right, that's all an FPGA, and it's just a USB that directly connects to the computer. But we still have the problem with the laser. So in this case, this is our laser head that sends out our light pulses and is a laser controller. That's a 1.5 Katana HP fiber amplified gain switch semiconductor laser. It's green. Of course, we would like to be in the invisible at some point. 5 megahertz rep rate. It has 1 watt of average power at full power. Send out 30 picosecond pulses. We would like better wavelengths, a smaller package, like some sort of semiconductor laser that can be manufactured easier, because this, if you buy it off the shelf, is about $80,000. So that still is not part of an iPhone. Current, like the iPhone LiDAR actually uses Wechsel arrays in the laser. These are kind of tiny little lasers that can put in the semiconductor, but they don't have short enough pulses. The pulse width is too long, so we can't use them. So we're still trying to figure out how to use what laser to use. Okay, and there is one other result that I wanted to share, which is, so we showed real time. This project is an attempt to improve the reconstruction quality using neural networks. I guess everybody doing research has to have a deep learning paper these days, so this is ours. So what we did here is, so we have our normal imaging system spat arrays. These are the two 16 pixel spat arrays that gave us our 28 pixels. And what we did is we just cut a hole in our relay wall and put a camera here. So now we can capture the non-nanosite transient data on the relay wall with our nano system, and it captures this like data cube of data. But instead of doing a reconstruction from it, we just store that, and we also simultaneously capture a picture of that same scene using just a regular photo camera hidden, like embedded in the wall, this one, right? So now we have a pair of, like, here's what the non-nanosite system sees, and here's a picture of the scene. So what we can now do is we can train a neural network to reconstruct this photograph given this non-nanosite data and see how well it can learn how to do that. We just have to capture a lot of training pair examples. So the students had to go and like put lots of different objects in different configurations in front of the scene, capture this data like transient and camera, and just create this database. Actually, I think it has about 400 training pairs in our database. And we then use that to train a neural network to do this reconstruction. And that works reasonably well. So this is an image of this is the ground truth. So this is photographs of the objects that we put into the hidden scene. So it's the letters 2 and 4 in different configurations. There's a teddy bear here and a guitar in a box. This is an example. I think we had 15 objects in lots of different poses and like combinations. I forgot the exact number, but basically that gives us our 400 different training scenes. And then if we try our old like reconstruction algorithms I want to describe, that is this wave imaging, these scenes are pretty challenging. That algorithm doesn't really get much. It can do the letters fine. I've shown you letters before, like it's fine with flat surfaces. This teddy bear, maybe you can still make out something here that just looks like the teddy bear. The box is really hard. If it faces like this, we know that our algorithm has really problems with surfaces that are not facing the wall. So these surfaces at oblique angles, they don't show up at all. And this guitar doesn't show up very well. So you don't really see much, except if you have this kind of cooperative targets like this letter 2. But the non-nanosite, the deep learning algorithm is doing really well in this case, in that it actually is able to reconstruct not only objects, but the details of the texture and everything. So this was really surprising, actually. We actually, in this paper, for a while, the student had accidentally put the ground truth images instead of the reconstructions, and nobody realized until at some point I looked at it, say, oh, why do they have the same noise? And then they fixed it. But these look so similar to the ground truth that it's like almost hard to distinguish which is the photograph and which is the non-nanosite reconstruction. Now, these ones are a little bit cheating because the neural network has seen this teddy bear as part of the training set, just not in this pose. So there is, in the training set that the neural network is trained with, there is that same teddy bear like upside down or in some other kind of configuration. And all the network has to figure out is how to put it and how the shadows are falling and everything. It's still impressive that it can do it, but maybe that's like, there's always the kind of this, and maybe it's getting the information from somewhere. And like, once you show it a different object, it will fail. But actually, so these are objects now that the network hasn't seen. The network hasn't seen this toy truck or any other toy that looks similar to this. It also hasn't seen this chair. It only has seen the numbers and stuffed toys and things like that I showed before. And you can see, again, our normal phasor field RSD algorithm really doesn't see much for these. But the network does really well, right? It can, like this chair is challenging, right? So, but it still reconstruct most of the details. Here it can see most of the beams. For the truck, it reconstructs this little label over here, which is way below the resolution limit of our old method. And it actually gets the geometry, it gets the view roughly right, it gets the shadows right. So this is, I'm really still impressed by this. And we're actually trying to figure out why it's doing so well. What is so much better about this training data than what other people have tried? So that is on side imaging. Basically, this is another example. Basically, we can upsample this teddy bear resolution to a higher resolution. So here's a ground truth image of the teddy bear, and here's a reconstruction of the neural network. And again, the network has seen the teddy before, so it knows what this fur looks like. So it really just has to see, okay, that's the shape of the teddy bear. It has this fur, but still it gets like these shadows correctly, right? And it gets like the pose and everything, and all these details are reconstructed very well, which is really impressive to me. So now let's look at some of the applications. This is going to be the last few minutes of the presentation, because I believe I'm kind of running out of time. So here are some of the applications we have been thinking about. Of course, like navigation, collision avoidance, self-driving cars. The car could bounce the light off the curb here. It could even bounce it off the road, right? And just to see around corners. Any kind of disaster response, right? Like fire department, like looking into a collapsed building where you have to locate people quickly and you don't have time to go inside. Like in this case, like there's something burning, you want to know whether there's somebody up there that needs help. So you could bounce the light off the ceiling and look into this space. Of course, military and law enforcement. There's actually a staggering number. I looked this up at some point. I mean, I did my 10 months of military service in Germany, and one of the things I learned is that one of the hardest things to avoid in these kind of situations where you're walking through the forest or through buildings is friendly fire, right? I think in some Iraqi cities, the friendly fire rate of the U.S. Marines was like 25%. So a quarter of the people that were killed by friendly fire, which is quite staggering. So you would like to know before you go in what's going on in there, right? Like you would like to be able to see people before they can shoot you, or you have to shoot them. It's basically the idea here. So that's where they'd be useful. Medical imaging would be interesting, right? You're very limited in terms of field of view in an endoscopy, for example, or in this case, cardioscopy. This one is hard, right? Because it's hard to bounce light off these surfaces in the body that are not, like they're very translucent actually. And it's also a very small scene, so you would need a very high time resolution to be able to do anything. The other one that I'll like talk a little bit more about in the minutes that I have left is this imaging of caves from the air. So this is something we actually seriously explored together with the NASA Jet Propulsion Lab on a grant. And the idea here is to look at these objects. This are images from the Lunar Reconnaissance Orbiter, which went up in the early 2000s. And they basically discovered, so it basically did a complete imaging survey of the moon, like the entire lunar surface at a high resolution, and it found lots of these objects that are hole in the ground, but it really doesn't look like the impact craters, right? So basically, you can see that there's an overhang. There are some examples where you have different perspectives, and you can see there's some parallax, so that there's really an overhang over there. There is examples of them collapsing along a line, which leads people to believe that these are entrances of caves that probably formed as lava tubes. So if there is any kind of molten rock due to a volcanic activity, the moon used to have volcanic activity a long time ago, or due to a meteorite impact, you would get like little rivers of lava that freeze over and then kind of empty out underneath, and then they can collapse in parts, and you get these lava tubes. You can find these on Earth in many places. Like New Mexico has parks like El Malpais with lava tubes. Hawaii, of course, has lots of them. So people think that's what they are. And if that's true, they would be great for a lunar base because they would provide shelter. Like the surface of the moon is not very hospitable. You have temperature, large temperature difference. You have radiation. In those caves, you're far enough underground, so you have to deal with none of that. So you could inflate a tent just to keep the oxygen in there and live there for extended amounts of time. The problem is, how do you explore those? There's about 200 of those that have been discovered. You clearly don't want to send a rover into one of them just to find that the entrance is collapsed or something, and then be stuck there. So the NASA is interested in surveying all of these to find a good site for a landing. And the idea was, well, we can use this Nonnanosite imaging system to just, from a satellite that would orbit the moon at a very low orbit, this is about as low as you can go, would image into the cave and basically see around the corner to see whether there is anything worth exploring in there. Our constraints are maximal 20-watt laser power. That's the most powerful laser that is currently in space. And that's part of the Atlas altimeter, which is used for LiDAR scans of the ice caps right now. IceSat is the satellite's called. We have a 10 kilometers distance. That's kind of the lowest orbit that you can create without running the risk of crashing into it. That gives us 15 seconds flyby from horizon to horizon because we're moving really fast. And unfortunately, the moon is not very reflective. We have less than 10% reflectance. So that was the constraints. And we found that we can't deal with direct sunlight, but we do have to deal with Earth shine. So we can actually image the caves on the Earth-facing side of the moon. Otherwise, you couldn't do that. So that was what we want to simulate. We actually, in order to simulate this in computation to see whether we can do it, we went and captured 3D images with a LiDAR scanner of an actual lava tube in New Mexico. Here is a picture of the lava tube. This is a big skylight cave in El Malpais. Great for hiking. You can actually do caving in there. They're not very big, big enough to get lost in. So you still have to take care, but not so big that you would need a guide to go in there. This is an example of the LiDAR scan. So here's basically this is a skylight here that we wanted to use. You can see the trees outside here. So we'd be imaging through this on the floor and try to reconstruct this cave. This is an example of the LiDAR scan of this exact kind of view down here. So again, this is a LiDAR scan of the ground truth geometry. We want to use this to simulate what the satellite would see through the cave, if it would image through this entrance, and then see whether our algorithm can reconstruct that. Of course, there's a lot of people involved in actually capturing this data. And here's some preliminary data for doing this. So we just assume that we have a really cool laser and SPAD array. And then just like this is a rendering of the cave. And this is what our reconstruction after capturing and reconstruction with a system like that would see. And you can see we can roughly get these shapes. We're actually limited here by our computation. We probably, if we can do this at the full resolution that we might have available or could in theory build, we could do this better. But basically, I mean, our goal in the future is to actually drive the applications on Earth far enough forward so NASA gets interested in actually kind of building something like this. This is all simulation, this project, but it does look like this could actually be done. So with that, I'd like to thank everybody for listening and conclude. There's a link to our website here if you want to know more. And I'm open to answering any questions you may have. Thanks.
Andreas, one of the things we were wondering about is when you were talking about the size of the pixels themselves, those are fairly large pixels at about 50 microns. Or are you talking about in the future trying to bring the size of those down a bit as you're adding more pixels?
Yes. So that's actually like, that's a good question. So those pixels, for this application, we wanted them as large as we can make them. And the reason for that is that for the non-Nonnanosite reconstruction, we need to know the location on the relay valve with about a centimeter resolution. So we would like to collect as much light as possible over a centimeter square. So we would actually want a really low spatial resolution. And if we are so close to the relay wall, the only way to do that is with large pixels. Like if you're further away, obviously you can just zoom out, but being so close, we'd either have to use very small apertures or very large pixels. So the reason why the pixels are large is because we wanted them to be large in order to collect more light. Now, the newer devices and newer sensors actually have smaller pixels, and that actually makes things a lot of things easier. One problem that these SPAD arrays have, actually don't know what the pitch of the, I mean, we have a megapixel SPAD array in the lab that is like C-mount, so it's centimeter by centimeter. So that has a much smaller pixel pitch. The big problem with this current generation of SPAD arrays is not so much the pixel size. That's flexible. You can make it as big as these, and also smaller. I think the reason why they haven't gone beyond like a few micron is because they don't have access to the higher resolution fabrication techniques that like Apple does for the iPhone or something. Those foundries just won't talk to you unless you offer to buy 1 billion sensors from them. So that's just a technical problem. The other problem is the fill factor. So what that means is with those pixels, so in a SPAD pixel, there is a lot of processing that needs to be done, right? So you have the actual diode that's light sensitive, but then you have to have a circuit that quenches it once it's hit by a photon, which means it lowers the voltage so the diode doesn't destroy itself, and then basically arms it again. You have to have the timing circuitry that actually times the arrival of a photon. You have to have memory to store the arrival time until it's ready to be read out. And that results in a pixel that where most of it is like logic gates and memory and stuff, and only a very tiny fraction of it is actually light sensitive. And that fraction is called the fill factor. And that usually for the current generation of sensors is around 10–20%. You can make that bigger with lenslets if you have a limited aperture size. And the way to fix that will be 3D stacking. So they actually already, the next generation is gonna have all of that behind the pixels, but they have to figure out how to actually stack 2 layers of semiconductors together accurately enough to do that. But so that's the thing, like the size of the pixels, in this case, we wanted them to be big. Making them smaller is technically not a problem. Right now, all these sensors, and that's also why probably for astronomy, where you're very, very concerned about the overall quantum efficiency of your sensor, and that's the fill factor is gonna be very, very detrimental, because like if only a very small fraction of your actual sensor is light sensitive, you're not going to be very efficient in detecting your photons. But that's going to go away. All of these things are solvable with this technology, with electronics, and it's going to happen. I think this field is developing fairly quickly now. So I think a few years from now, actually, this Canon array already announced a almost 100% fill factor, like 80% or something, and fairly high quantum efficiency. So at some point, the single photon sensors, you will be able to have them at the same pixel pitches and the same fill factors as a regular camera. But again, you probably don't want to use them unless you want things to be fast.
Right, and I would think the computational time for having a lot more smaller pixels would be a limiting factor too.
That is actually, so we've just written a few papers, or we're writing papers, and there's other papers. That is actually I feel like that's for this entire field of SPAT array imaging, from a computational, from a data point of view, that is the interesting challenge, right? So basically, you in order to do imaging with these, you have to process all the photons. Right, so it's really like how much data can you actually get out of these, and you can easily, if you have a megapixel array, and our SPAT now can detect and time tag 1 photon every 100 nanoseconds. So if you have a 16 megapixel array that detects a photon time tag, 1 byte photon time tag every 100 nanoseconds, you would end up with tens or hundreds of terabytes of data per second. So the key is going to be to come up with algorithms on methods to compress that in a way that you don't have to read off all of that. So a lot of, and basically the existing high resolution arrays do that in a way by just either capturing very, very low temporal resolution or low spatial resolution, or combining information from multiple pixels, or like the 1 megapixel array we have doesn't actually give you the timing information. It gives you just really high frame rate binary data, photon or no photon. And that's all because you just don't have the bandwidth to transfer all the information that you could capture.
Mm-hmm. Thank you.
Do we have any more questions? Well, Andreas, on behalf of Madison Astronomical Society, I'd really like to thank you for this really eye-opening presentation. And it's just, kind of mind-boggling to think about light this way. And multiple times, a few times during the presentation, I was also thinking about bats and what applications sound might have for something like this, if at all possible. And I'm thinking about all the computations and things that the brain of a bat's able to do. And it's amazing the amount of effort we put into these kind of computations to be able to interpret light with these kind of applications. It's just really amazing.
We did at some point like get interested in the question, can bats see around the corner, right? Because I don't think anybody has ever tested whether they, because they do see these multiple reflections. It's just a question whether their brain is able to analyze that and make sense of it if there's something around the corner. But that I feel like if there's anybody that knows a bat biologist that could test that.
Yeah, that'd be fascinating.
Yeah, I'm interested to see the first 3D rendering of a nebula.
Well, yeah. So you could do that with, so if you use a flash from a supernova, you could try to do a LiDAR reconstruction of the nebula.
That would be interesting.
Yeah. Don't know whether one supernova would give you enough light. An interesting question.
Yeah. Well, all right. It was great visiting and seeing everyone tonight, and it was great to be here for this presentation. And join us again next month on March 11th, Friday, March 11th at 7 o'clock.
Thank you.
Andreas, we hope to, hopefully, I'll have to, if in case there's anything like this on the web that we see about this kind of technology moving forward, we look forward to that.
Yeah.
Well, good night, everyone.
Have a good trip, Bonnie.